At the design stage, we want to design a pumping system that allows the pump to operate or work as close as possible to its maximum efficiency. However, when the pump is already being installed, we need to deal with some losses that occurs during the operational of the pump. So actually there are four main sources of loss in pump operations. So the first one is the mechanical loss. So mechanical loss is solely due to the frictions between the fixed and rotating parts in the bearing of a centrifugal pump, so to say. The second source is this friction power loss. So this friction power loss is mainly due to frictions between the rotating face of the impeller or the blade and the liquid. So this is actually due to friction between fluid and the rotating part of the impeller. So this one is between bearing and let's say shaft. The third source of the pump losses is due to leakage and recirculations from the working fluid inside the impeller, and this is also leakage and recirculation. So this is also one of the main sources for the pump losses. The fourth source of the losses is losses due to the casing of the pump itself, or we call it casing power loss. So all of it, let's say this is PC and this is PL and this is PI due to the impeller and this is PM for mechanical. The impeller power losses, or PI, can be attributed to the energy or head losses, or HI here we have, at the impeller due to these frictions, or it can be due to flow separations or shock of the flow at the impeller entrance. So let's say this is the impeller entrance. We have the drawing here. The orange arrows represents the fluid flowing into the impeller. This impeller power losses is also attributed with the flow rate of the fluid flowing through the impeller. So QI here is the flow rate of the fluid flowing through the impeller. So we have QI here inside the impeller. So the fluid flow inside the impeller, we call it QI. And therefore, the power losses at the impeller is equal to the density multiplied with gravity multiplied with the flow rate of the fluid inside the impeller and the head loss due to frictions at the impeller. As we know that when the fluid leaves the impeller, it flows at flow rate of Q. Here we have Q when the fluid leaves the impeller, and it is the functions of the fluid flow inside the impeller, QI, minus small q. So small q is the fluid being recirculated back to the impeller due to the casing here. So this recirculation can also be attributed or it can be associated with leakage phenomenon inside the centrifugal pump. So the losses due to the leakage, or we call it leakage power losses, or we can write it down as PL, so this is L, and it is a function of PL equal to density, gravity, HI, and Q, small q, due to the recirculations inside the impeller casing. So the capital HI is the total head across the impeller. The last source of losses in the centrifugal pump can be attributed due to the casing power losses, and it is the functions of density, gravity, the fluid flow rate outside of the impeller or at the outlet of the impeller, and the head loss at the casing, or HC. So this is the casing power losses to overcome all of these source of losses. The shaft of the pump that deliver power to the impeller has to overcome all of the sum of these losses. So we have mechanical losses PM plus all of these source of losses, the impeller losses, casing power losses, and leakage power losses are functions of density and gravity, and then we add the functions of HI, small h, multiply with QI, which is the impeller power losses, plus HC multiply with Q, which is the casing power losses, plus capital HI to multiply with small q, which is the leakage power losses, plus capital Q multiply with H. So this is the total head that delivered by a pump. So these equations we have earlier on this tutorial video. So PS is the total power by shaft. So this shaft is being rotated by an electric motor. So this is the amount of power of an electric motor has to transfer to the shaft, and the shaft will transfer it to the impeller of the pump. So this is where we will have the overall efficiency, which is a function of fluid power developed by pump divided by shaft power input, or mathematically we can write it down as rho gravity capital Q capital H divided by PS, or shaft power input. So PS is from this one, and this is the fluid power developed by the pump. As we already discussed about the losses occurs on a centrifugal pump, so these losses lead us into the efficiency of each losses. So we have casing power losses, and now we have the casing efficiency, or is a function of the fluid power at the casing outlet divided by the fluid power at the casing inlet. It is a function of density, gravity, flow rate multiplied by total head divided by density, gravity, flow rate divided by the head power loss at the inlet, or it can be written as, we can eliminate the rho G and Q, and it left us with H divided by HI, where HI is the total head across the impeller. So we get this one previously from the leakage power loss. And the second one, the second efficiency is the casing efficiency. Sorry, I mean the impeller efficiency, which is a function of the fluid power at the impeller exit divided by the fluid power supplied to the impeller. So this is a function of density, gravity, Q, the flow rate at the impeller, and the head at the impeller divided by the density, gravity, Qi, the flow rate at the impeller, multiply with the sum of or the total of the head at the impeller and the small hi. The small hi, if you remember, is the energy or head loss in the impeller due to these frictions, flow separations, or the impeller entry. So we find the small hi before at the impeller power loss. So due to the impeller power loss, we have this impeller efficiency, and this is a function of capital HI, which is the total head across the impeller divided by the total head across the impeller plus the impeller power loss or energy losses at the impeller. The small hi is the energy power loss at the impeller. The third part of the efficiency is called as the volumetric efficiency, or NV, that is functions of the flow rate through the pump divided by the flow rate through the impeller. So we have the capital Q as the flow rate through the pump divided by the capital Q plus the small q, which is the amount of fluid being recirculated inside the impeller. So this is the volumetric efficiency. And also we have the mechanical efficiency, which is the functions of the fluid power supplied to the impeller divided by the power input to the shaft. And it is the functions of the density, gravity, Qi, or the flow rate inside the impeller, multiplied by the sum of the head loss due to frictions of the impeller plus the capital HI, which is the total head loss across the impeller. So this is the functions for us to get the value of mechanical efficiency. And by summing all of this efficiency, we get the overall efficiency of the of any centrifugal pump, which is the NO, that is equal to NC plus NI, multiply with NV, multiply with NM, or the mechanical efficiency. So we multiply all of them to get the overall efficiency of a centrifugal pump. And also we have the hydraulic efficiency, or NH and capital H, which is the functions of the total head across the pump, capital H, divided by the total head across the impeller, capital HI, plus the energy loss due to frictions at the impeller, or small hi.